Welcome to Empowered Learning. This is the second video in a video series for techniques of integration, where we are studying partial fraction expansion and how we use that to be able to evaluate integrals of rational functions. So our next example that we have here, we see that we have a rational function where the degree of the numerator is smaller than the degree of the denominator. So we want to try to factor out the numerator and denominator as much as possible. So starting this example here, we see that we have a common factor of 2 in both terms in the numerator. So we're going to go ahead and factor that out. And what we have left in the numerator is x squared minus 7. In the denominator, we can factor that out to x squared minus 1 times x squared plus 1. And of course, all of that will be times dx here. So we can continue on. We'll see that the denominator for this, the first factor in the denominator here can be factored out some more to x plus 1 times x minus 1. But we have that irreducible factor, x squared plus 1 here. So that's part of the reason why this is a case 3 type situation, because we have an irreducible quadratic factor here that we have to deal with. So now that we're here, we realize that, hey, we have 3 factors that are in the denominator that are all different from each other. We do realize that we have this x squared plus 1 there, so it's going to make things a little different. But we can essentially break this out. In other words, we can take our integrand here, and we're going to try to break it up into some form of partial fraction expansion. Now, how we deal with this, being that we have our rational function factored out and it looks the way that it does, for these first 2 factors here, we'll just do this as we had in the part 1 video. We'll just say a divided by x plus 1 plus b divided by x minus 1. Now, for the quadratic factor here, what we have to do is, in the numerator, we have to write an expression that is 1 degree lower than what the degree of this particular factor is. So since x squared plus 1 is of degree 2, then we are going to have to write a general linear expression of degree 1, which will look like this. So that's how we actually deal with those irreducible quadratic factors there in the denominator. Now, the good thing about what we have here is that for the answer to A and B, we can do it via that short way that I showed you in the part 1 video. The bad thing here is that that's not going to necessarily work for solving for C and D. Okay, so there are 2 strategies that we can take here. One is that we could do this the long way. And so what that would look like is just basically taking what I have here and forming it into one big quotient, and then just making the numerator on the right hand side here equal the numerator on the left hand side, and breaking it out in terms of all things that have x cubed in it, all things that have x squared in it, all things that have x in it, and all things that are constants. So we can go that method, or what we can do is we could utilize the shortcut method that we have and find out A and B, but the cost that we're going to have to pay for doing that is that now we have to do algebra to basically take these 2 expressions with A and B in it and subtract them from both sides, and then work with the arithmetic manipulation here to eventually get something that's going to look very similar to cx plus d divided by x squared plus 1. Okay, so since we in the part 1 video, we kind of already know how to take this 3-term expression here and to form it into one single quotient and then break it out. I'm going to do this the other way that employs finding A and B the shortcut way, but then having to do the algebra by subtracting both of these terms from both sides here to eventually getting something that's going to mimic cx plus d divided by x plus 1. So that's what we're going to work on here. So let's find out A and B first. So A is simply going to be everything that I have here in my quotient except for the x plus 1. So we're going to have x squared minus 7 here divided by x minus 1 times x squared plus 1. And we're going to evaluate that at the value of x that makes the denominator for the a for the a constant that we're trying to find here. That denominator, if we plugged in a -1 for x, that would make that go to 0. So that is what we're going to evaluate that by. So then it's just a matter of just plugging in to see what our answer is going to be. So we go ahead and plug in -1 everywhere where we see x. In the numerator, that's going to give us a -6. In the denominator, we'll have a -2 times 2 here. And that looks like that's going to give us negative divided by negative is a positive here. And we'll reduce there, so that'll give us a 3/2. Okay. So that is what our A is. So our B, we're going to find it in similar fashion. So B has a denominator of x minus 1. So we want to forget about that in the denominator, but write everything else. And then evaluate it at the number that makes this denominator go to 0 here, which is going to be x equals 1. And so again, we just plug in 1, figure out what corresponding answer will be. So in this case, we end up with a -6 divided by 2 times 2, which this will end up being a -3/2 in this case. So you see here that A is 3/2 and B is a -3/2. So now that we have that, then we know here that, of course, A is 3/2, B is -3/2. And so now our goal here is we need to find out what C and D are, but we can't use this shortcut method to do that because this only works whenever you have a situation where you have linear factors in the denominator. Okay, so in other words, here, because of the fact that I can't say here I have CX plus D and then try to do the same thing I just did for A and B there. This technique won't work for that. Okay. So here, what I'm going to have to do is, I'll switch colors again here, is I'm going to have to say x squared minus 7 divided by this x minus 1 times x plus 1 times x squared plus 1. And this term I'm going to have to subtract from both sides. So I'm going to have a -3/2 over x plus 1. And this term I'm also going to have to subtract from both sides. So since that's already minus, when I subtract it, it's going to be a plus 3/2 x minus 1. And all that is going to equal to cx plus d over x squared plus 1. And so now my goal here is to figure out what the left-hand side is going to be so that I'll know what C and D are going to end up being. So to do this, the very first thing that I'm going to do that's going to help make the arithmetic a little bit easier here is, since I have these fractions that I'm dealing with here, I don't really want to deal with that. So what I could do here is I could rewrite this fraction of 3 divided by 2 in the numerator as 3 and then put the 2 in the denominator. Okay, and so by me doing that, that's going to make this look a little bit better. So I'm going to go ahead and erase what I have here, and I'm going to go ahead and implement that. So we'll have this, put the 2 there, and we'll do the same thing for the other. So again, it's what I'm doing is it's the exact same thing. I'm just making it look different here. Okay. All right. So now that we have that, we know that we're going to have to find a common denominator here. Okay. So to find a common denominator, I look and I know it's just basically going to be all these factors, the x minus 1 times x plus 1 times x squared plus 1. But I'm also going to have a 2, since I've introduced that 2 in these other 2 terms. So to help me out here, I could also multiply this first term by 2 divided by 2, and I can make it look like this. So that way, now I have the 2's in all of the denominator. And so now all I need to do is figure out, well, hey, how can I make these 3 terms into one big quotient? And so we will figure that out. So for this first term, I have everything, so there's really nothing else that I need to do here. So all I'm going to do is just distribute this 2 to both terms. Okay. And notice here that my denominator for all of this is going to be what I have here. Okay. Now for my second term here, I know that I have this minus 3, but I know that the only thing I have in the denominator is the x plus 1. So that means everything else that I see in the denominator here other than the x plus 1, I got to multiply it times the negative 3 there. So if I do that, then I'm going to multiply the negative 3 here by x minus 1 and a x squared plus 1. And of course here, I forgot I actually have a 2 down here as well. So I don't have to multiply the numerator and denominator by 2 since I already have the 2 down here. So I basically have these 2 covered. Sorry, I underlined the wrong ones there. So let me do a different color here. So I have the 2 and I have the x plus 1 covered in this term. So that means everything else that I haven't underlined, I have to multiply it times the negative 3 in the numerator. Okay. Now, if I do a similar thing with the last term that's on the left-hand side there, let me erase this. Then I have the 2 and I have the x minus 1. So whenever I take this plus 3 right here, I need to multiply it times what's left. So I have the 2, I have the x minus 1. So I need to multiply it by x plus 1 and then x squared plus 1. Okay. And then all that has to be equal to cx plus d, all that over x squared plus 1. Now, what we are expecting here is that once I multiply all this out and I combine like terms in the numerator, that everything except for that x squared plus 1 should eventually find a way to be able to reduce itself with factors that are in the denominator, so that all I have left is the x squared plus 1 in the denominator, And then whatever I have in the numerator here, it should be some term times x plus another term, which would be a constant. And so from that, I can extrapolate out what's going to be my C and D values. Okay. So let's go ahead and do that now. So I have 2x squared minus 14. Let me not distribute that yet. So here we will have a minus 3 times x cubed plus x minus x squared minus 1. And that's just me foiling the x plus 1 and the x squared plus 1. And then we'll do the same thing here. We'll have x cubed plus x squared plus 1. Of course, all that will be divided by our denominator here, which is not changing. So from here now we need to go ahead and distribute the 3 to all of these terms here, and the 3 to all of these terms here. So we'll get 2x squared minus 14 minus 3x cubed minus 3x plus 3x squared plus 3, and then plus 3x cubed. Then plus 3x plus 3x squared plus 3. And all of that still divided by the same denominator here. And then we have cx plus d is equal to x squared plus 1. All right, so now that we have all this multiplied out in the numerator, on the left side, we can now see what is going to cancel. So I can see now I have this minus 3x cubed and positive 3x cubed. That cancels. I also have a negative 3x and a positive 3x. And so I look, and it doesn't look like anything else cancels, but now I can combine like terms. So looking here, let's use this color. So I have all of my terms with x squared. So I have 2x squared, 3x squared, and another 3x squared. That is going to give me 8x squared. So I got 8x squared here. And then I have a minus 14, a plus 3, and a plus 3. So that's minus 14 plus 3 is minus 11, and minus 11 plus 3 is a minus 8. And of course here we have this 2 times x minus 1 times x plus 1 times x squared plus 1. And that will be equal to all this. And so hopefully now you start to see where this will end up not canceling, but having factors that reduce to 1 here. So if we take our 8x squared minus 8, we know that that could work out to 8 times x squared minus 1. But of course, our x squared minus 1 is the same as x minus 1 times x plus 1. So we're going to go ahead and write that out. X minus 1 times x plus 1. And then we just have 2 times x minus 1 times x plus 1 times x squared plus 1, all in the denominator. And all that now is equal to cx plus d over x squared plus 1. And now we start to see the light. So here, the x plus 1 factors reduced to 1. The x minus 1 factors reduced to 1. And 8 divided by 2 ends up being 4. And so what we end up with here, and I'm just going to write it here in black, is just 4 over x squared plus 1. And so from this, we see that all we have is a constant term. So if we wanted to write this out explicitly, this would be like a 0x plus 4. So here, this would be like 0x plus 4. So what this tells us here is that our c is 0 and that our d is 4. Okay. Now, this was a bit of a process, but I did want to show you that because this is a technique that we use. For this particular problem, it really just kind of depends upon how comfortable you are with the different methods. This method may be faster than just kind of putting everything together way up here at the beginning as just one quotient and doing systems of equations. Some people may feel more comfortable doing that. Other people may feel comfortable doing the method that I did here. But I at least want to showcase this method because I haven't shown it yet. Okay. All right. So now that we know what C and D are, then we have everything that we need. So I'm going to copy this down here. We have A is going to be 3 over 2. So let's try that. So A is 3 over 2. And B is a minus 3 over 2. And so now we take our expression here, and it's just going to be 3 over 2 divided by x plus 1 plus or minus 3 over 2 divided by x minus 1. And then for this cx plus d, this is just going to be 4 divided by x squared plus 1. So I'm going to scroll down, I'm going to write all that out, and then finish up this problem. And let's do a different color here. Finish up. So therefore, we know that if we take the integral of 2x squared minus 14 divided by x raised to the 4 minus 1 dx, then we know that we can essentially rewrite this as 3 over 2 divided by x squared plus 1. And let me make sure that that's right. Yep. And then we have a minus 3 over 2 x squared minus 1. Then we have the plus 4 divided by x squared plus 1. And so now from here, it's pretty smooth sailing from this point. So for the first term, we have a 3 over 2. Antiderivative of 1 over x plus 1 is just natural log of absolute value of x plus 1 minus 3 over 2. Natural log absolute value of x minus 1. And then we'll ignore the 4 here. And of course, the antiderivative of 1 divided by x squared plus 1 ends up being a tangent inverse, or arctan of x. And then we just have plus c there. And I'm going to try to make that arctan look a little better. Okay, and so technically that is our answer. Of course, we could simplify this and make it be a bit more compact, but essentially that is it. I'll go ahead and do one more step here and just rewrite this as 3/2 times natural log of x plus 1 divided by x minus 1 plus 4. I'll write it in this form too. So tangent inverse, you can also write it that way, plus c. And so this is good enough at that point. Okay. So that is how we work this example when we have a case 3 situation, which is, again, case 3 situation is one where we are dealing with some quadratic factor, irreducible quadratic factor in our denominator. All right, so this will be the last example for this particular video. I'll make another video covering the other examples that I told you about in the part 1 video. But for this one, I wanted to close out with this one because of the fact that it has some of the elements of the previous example, in that we're going to have an irreducible quadratic factor that we're going to have to deal with. But also for this one, if you notice, the integrand has a numerator that has a polynomial that has a degree that is higher than the degree in the denominator of the rational function that we're dealing with here. So because of that, we're going to have to start this process off by actually doing polynomial division first before we do anything else. And so this will give us a good chance to review polynomial division, just in case you're a little shaky with that. So we have this particular integrand here that we're going to deal with. And let's start off with this color here. So we will just say y cubed plus 4y. And we're going to divide that. We're going to take the y to the 4 plus 4y squared minus 1 and divide it by the y cubed plus 4y. So when we do this, of course, the first thing that we ask ourselves is y cubed times what give us y to the 4th? And that is just going to be y. So now that we know that, we're going to take y and multiply it times y cubed, and that will give us y to the 4th. And y times 4y, that's going to give us a positive 4y squared. And so now what we need to do is, since we have two positive terms here, we need to subtract, just like how we would with normal division. And so in doing that, we know that the y to the 4 terms cancel. We also see that the 4y squared terms also end up canceling. And all we have left here is a -1. And so when we bring this down, and so because we have that, and we know that y cubed times what give us -1 will actually be something that's not a polynomial, we can stop. Okay? So this was pretty simple here. So therefore, we now can rewrite our integrand that we have here essentially as the following. So I'm just going to say equals. So now we take our quotient, which is y, minus, and then we're going to, of course, have the 1 over y cubed plus 4y. So that is how our integrand can be rewritten. So now that we're here, of course, integrating the first term is relatively simple. The second term is going to take a little bit of work. And so what we know here is that we could factor out a y out of both terms in the denominator there. And if we do that, we'll end up with y times y plus 4 in the denominator for the second term for our newly rewritten integrand. And so now you see how we have that irreducible quadratic factor that we're dealing with. And so what we need to do here is go ahead and see how we're going to break this part out. Okay, so we're going to do it very similar to how we did before. So this is the portion that we're going to concentrate on here for just a second. But before we do that, I'm just going to go ahead and handle this first part here. So we know that the antiderivative of y is just going to be 1/2 y squared. So we'll say that minus integral of 1 over y times y plus y squared plus 4. And that would be dy. So just for clarity here, I'll just write it like this. So this is what we want to rewrite. Okay. So I'll put note. We know that 1 over y times y squared plus 4. If we follow partial fraction expansion techniques here, we can say that this is a divided by y plus by plus c over y squared plus 4. And so now we just need to figure out what that following result is going to be. So we'll start off by figuring out what a is. We'll use the shortcut method for that. So we'll just say a is going to be, and we'll keep everything except for y in the denominator here. So this will be 1 divided by y plus 4. And we will evaluate that at the value that makes y go to 0 here. Well, it makes this denominator, which is y goes to 0, which in this case is 0. So that's just 1 over 0 squared plus 4, which ends up just being 1/4. So we know here that our a is just 1/4. So that means here this is going to be replaced with a 1/4. And so now what that also means for us is that we need to subtract this 1/4 divided by y from both sides here so that we can have the by plus c divided by y squared plus 4 by itself. So we do that, then we'll say therefore, and matter of fact, I'm going to switch colors here. So therefore, have 1 divided by y times y squared plus 4, and then we'll subtract that 1/4 divided by y, and all of that is going to be equal to by plus c, all that divided by y squared plus 4. Okay. And so now, just like how we did with the last example, we need to make the left side look like the right. And so the first thing that we can do here is I'm going to rewrite this 1/4 so that I have the 4 in the denominator and just the 1 in the numerator there, because that'll again help me out as far as getting this looking like the way that I want it to. So here we'll put the 4 here and the 1 there. And so we need to have a common denominator in between this y times y squared plus 4 and 4y. So another thing that we see is that both of these denominators are going to have a 4 here. So what I can do is multiply the numerator and the denominator by 4. So I can take care of that part. And so now we see that the last thing that's left here is that both of these denominators have 4y, but the second term is missing a y squared plus 4. Okay, so here what I'm going to do is erase the numerator here, and we're going to put in that we have 1 times a y squared plus 4 here. And so when we do that, this implies that, let me put the y squared plus 4 in the denominator there. Matter of fact, let me make that a different color so that we know that that's something that we've included. All right, so I'll put that in black just like how I did the other one. So now that we have that, our result here is going to end up looking like 4 minus y squared plus 4, all of that over 4y times y squared plus 4, and that is going to equal to b y plus c over y squared plus 4. And so now all we have to do is distribute this negative to both terms here. And if we do that, what we see that we come up with is a 4 minus y squared minus 4 all over 4y times y squared plus 4. And we see that those 4's in the numerator on the left-hand side will end up canceling, which essentially just gives us a negative y squared on top. So of course that cancels here. And so we see that what we end up with here is a negative y squared on top. But notice that we have a y squared here and a y down here. So this is actually going to reduce, and we're just going to have a minus y. And so finally, what we can do now is to make this denominator and this denominator match. I can bring the 4 back up to the numerator. So now that I have a negative 1/4 times y over y squared plus 4 equals by plus c over y squared plus 4. And what that ends up being here is that b ends up being a negative 1/4, and c, since we don't have anything here, we can put a plus 0, so c ends up being 0. So we know what our a is now, and we know what our b and our c has to end up being. So we'll come back up here. Now that we know what this is a minus 1/4 here, and this is going to be 0. So now all we need to do is just copy what we have up here, take the antiderivative of it, do our plus c at the end, and then we're done. All right, so therefore, if we start out from the beginning here, we had the integral of y to the 4th plus 4y squared minus 1 all over y cubed plus 4y dy. And we know that we can just rewrite that now as just 1/4 over y minus 1/4 y squared plus 4. And let's make that 4 look a little better there. All right, and there's a y that is supposed to be here that I forgot to write. So, all right, so now that we have that, then I'll go ahead and put this all in here, then do integral sign dy. And so now at this point, we just need to integrate both terms. I'll write this out. 1 over y dy. This will be a minus 1/4 integral of y over y squared plus 4 dy. So for this first term, it's relatively simple. We know that it's just going to be natural log of absolute value of y. No big deal. So for the second term, we know that we could use substitution. So we'll go ahead and do that. So let's, in this case, let W equal y squared plus 4. So if we let W equal y squared plus 4, then that means that dW is going to end up being 2y dy. And what we want to be able to cover is y times dy. So that's going to be 1/2 of dW is just going to be y dy. Okay. So we could rewrite this particular interval here in terms of W. So we're going to go ahead and do that now, and then we will wrap this up. So I have 1/4 natural log of absolute value of y minus 1/4, and then we know that y times dy is just 1/2 dW, all that over W. Then we'll say 1/4 natural log absolute value of y minus 1/8 natural log of absolute value of W plus C. And of course, W is just going to be y squared plus 4. And so this is our final answer. Of course, we could collapse that into one logarithm if we wanted to, but it's not necessary for us to do that. So just leaving it as 1/4 natural log of absolute value of y minus 1/8 times natural log of absolute value of y squared plus 4 is fine. And this is a subtle thing. We could actually drop the absolute value signs on the second term, since y squared plus 4 will always be non-negative. But we don't know what y would be, so we would need to keep the absolute value signs there on that one. All right, so this concludes the second video in the video series on integration techniques where we are employing partial fraction expansion. So I'm going to record one more video, and this video will go through some of the more involved problems that I wanted to deal with. And most of these will already be worked out. And again, the purpose of showing you these is to show you how we deal with more complicated type situations. And just know that if you're going to watch that third video, that you're more worried about the flow in which the problems go versus all the minutia that may be in the problems. Okay. All right. So hope to see you there.